Good morning. First, I would like to thank Dibubam for inviting me to give this talk today. I'm Mohamed, a research fellow at University of Surrey, and today I will give you a quick overview on the SpaceNet testbed that we built at University of Surrey. So first, I would like to start this presentation by a bit of a background to set the context. So internet from space is not new. We already knew that few decades back when we start sending and building geostationary satellites in the space. With a handful of geostationary satellites, we can cover the entire Earth and provide internet access anywhere. However, these geostationary satellites have a fundamental drawback. They are at 36,000 kilometers away from the Earth's surface, which makes the round-trip latency between these satellites and any ground station or terminal to be around half second. And obviously, this is a very high delay and way beyond the today's application requirement like video streaming, video conferencing, or even gaming. But not only that, it's also because these satellites are so far away from the Earth, new technologies like beamforming might be difficult or even expensive to be implemented in these geostationary satellites. 4 or 5 years back, we started to see plans that will significantly change the internet infrastructure in the space. So several competitors are working on sending thousands of small satellites to the low Earth orbit and forming what they call mega-constellations and blanket the whole Earth or the entire Earth with a low latency internet services. So motivated by the cost reduction in the satellite component manufacturing and also the lower launching cost, so the race to send tens of thousands of these LEO satellites has started already. So these satellites will not only provide low latency and high bandwidth or high speed broadband, but it will also enable a new class of application that is currently not viable by existing internet infrastructure. So I'm talking here specifically about the algorithmic trading between two faraway cities, something like Tokyo or Johannesburg and New York. So this is currently not viable by existing infrastructure. However, planking the entire Earth with a low latency and high speed broadband is not as easy as we just say it now. There are special characteristics and key challenges that make these LEO mega-constellations different than geostationary satellites or any connectivity in space that we knew so far. So let me here start by listing some of these challenges, and I will start first by latency. So high latencies are no longer an issue on LEO satellites. As I mentioned, because these satellites are much closer to the Earth compared to geostationary satellites, so they don't experience high latencies or high round trip time. Rather, the internet traffic passing through LEO satellites can experience frequent changes in the latency or abrupt changes in the latency. But why this is a problem? Simply because high variation in latency can negatively impact some applications like video conferencing or gaming or any application that is sensitive to jitter. Now, there are different reasons for that abrupt or frequent change in the latency. So one thing could be the change in the route that the traffic experience passing from the source to the destination. And this is for nothing but just because these satellites are nothing but routers in the space. But they are mobile routers. They are not stationary routers as we know in the internet backbone now. They are mobile routers. So mobile routers means that the location change over time, and that means their routing table as well change over a period of time, over a short interval of time, and that cause specific routes to be changing over a short period of time, which means the internet traffic passing through this route will experience different latencies, and that is what causes this high variation. But another reason could be also the handover between from one satellite to another satellite. So the terminal or the ground station has to decide on which satellite to connect to on the space. The terminal can see 5, 10, or 20 satellites, and they have to choose one of these satellites to attach to. But not only that, after some period of time, it has to switch from one satellite to another satellite. Now, I might be connected to the very far away satellite, and that be causing me some latencies. But now I'm reassess my situation as a terminal, and I'm connecting the nearest satellite, and that will reduce my latency. So again, there's a abrupt change in the latency here because of the handover from one satellite to another satellite, and this is mainly lead us to the second challenge, which is the terminal satellite handover. As I said, how the terminal decide to which satellite to connect to. So the handover concept is actually not available in the geostationary satellites, simply because of the wide coverage print of these satellites and the low speed of these satellites. So a geostationary satellite takes something around 23 hours and 56 minutes to complete one orbit around Earth. So this is around like 24 hours. And they are traveling at exactly the same rate as Earth, which means a terminal or a user on Earth actually sees these geostationary satellites as a fixed satellites. And that's explain why there is no handover concept here in this geostationary satellites. However, this is completely different in LEO satellites. In each LEO satellite, it takes around 95 minutes to complete one orbit around Earth. So this is like 1.5 hours to complete one orbit around Earth. But not only that, but also a LEO satellite can be visible for a terminal or a ground station on Earth for a very short period of time, something around 5 to 10 minutes. Therefore, designing an efficient handover mechanism is crucial for LEO satellites to maintain seamless connectivity moving from one satellite to another satellite. So what does this efficient handover mechanism mean? It's a very open research question. It could be based on the distance. So I get connected to the nearest satellite, or it could be based on throughput, based on interference, could be based on the longest attachment. So the terminal choose to attach to the satellite that will remain connected to for a longest period of time. So this is still a very open research question, how to design an efficient handover strategy. And then the third challenge is actually routing. So as I mentioned, these are mobile routers. These satellites are just nothing but mobile routers. Now, the key question is how to design a routing protocol that can quickly detect the route changes and propagate these changes to all the satellite and the mega constellation. Or let me put it in another word, how to design a fast convergence routing protocol. And when we talk about routing protocol, we cannot ignore things like traffic engineering, which aim to avoid causing congestion on specific routes. So there are a lot of challenges, and there are a need to start rethinking and testing existing or experimenting with existing routing protocol, existing internet protocol on this LEO network to understand how efficient these existing protocol are, and do we need to adapt them or redesign them from scratch to be deployed on this new paradigm of LEO Mega-constellations. And this is one of the key motivation of why we need to have Emulator, is to be able to design, not only design, but also experiment with existing protocols to see how they perform and understand their performance on this LEO network or LEO mega constellation, and then maybe redesigning or re-implementing a new protocols that would be more efficient on these mega constellations. But it's not only about designing or coming up with a new routing or with a new protocols, but also it's about planning a new consultations. So sending 1,000 satellites or even 100 satellites to the space is a very expensive and extremely expensive process. Now, if you can emulate this new mega consultations before in a more like a realistic environment and test its performance before sending any satellite to the space, you're trying to minimize the cost of due to any error or any inefficiency. So this is another key motivation why we need an emulator. We need to test any consultation in a realistic environment before we send it to the actual space and spend a huge amount of money due to error or inefficiency. So another thing is actually Emulator can enable us to assess the performance of the LEO Mega-constellation on a large scale. So for example, if you want to understand the performance of Starlink Mega-constellation in, like, let's say 100 locations distributed over the globe. So that means you would need to deploy or get access to around 100 Starlink terminals to run that performance measurement or performance measurement experiments on these terminals. First, that can be very expensive, and also that can be time consuming. Now, if there's an alternative approach in which that you can emulate these 1,000 or 100 locations in a realistic environment and get the same performance as in a real deployment, that could be more efficient way of doing that on a large scale. So I will talk later on how we can guarantee this emulator that we built here is actually a realistic or can provide a realistic environment. So another thing also that motivate the need for to build an emulator is actually enable researchers to test and maybe design a new scenarios that hasn't been already deployed in the existing real network. And a clear example of that, the inter-satellite links of Starlink. So if you'd like to understand how inter-satellite links will change the game and minimize the end-to-end latency and that LEO network, we cannot test that now simply because Starlink hasn't activated the inter-satellite links on a large scale yet. So we cannot understand the significant impact that this future scenario would bring to the LEO network. The only way to do that is actually to emulate it in a realistic environment or using a realistic emulation. And this is another motivation why we need such emulator. Okay, in order to achieve all of that requirements and all of these scenarios, implementing new design, new protocols, plan new consultation, do large-scale deploy measurement studies, and or even experiment with the future scenarios, the emulator has to be actually or has two features. It has to be scalable and it has to be realistic. So let me start by scalable. So scalability in the sense that it can emulate thousands or even 10,000 of satellites and ground station in real time. And real time here is actually a keyword, which means that a 1 second simulation time or virtual time should be actually should correspond actually to like 1 real second or 1 wall clock second, or at least close to that, to 1 real second. So if I want to simulate like 100 second or 200 second, that should correspond to 100 real second or 100 wall clock second. And this is what we mean by real time. The second point is actually the emulator has to be realistic. But what do we mean by realistic? Realistic is actually how comparable the network performance and this emulated LEO constellation that we emulate to the real world measurement that we collect, for example, from the live LEO Mega-constellation. So for instance, if I have a real Starlink terminal in London, and I'm testing the downlink throughput on that terminal. So I'm collecting downlink throughput on that terminal, which is connected to Starlink Mega-constellation. So if I want to emulate that terminal and the Starlink Mega-constellation in this emulator, now how that downlink performance or downlink throughput performance is comparable to the performance in the emulator when I'm emulating the same terminal location and the satellite and the Starlink Mega-constellation. So this is what we mean by realistic. It has to be the performance of these two environments, the real one and the emulated one, has to be very close in order to guarantee this realistic behavior. I will talk in the coming slides how we achieve this realistic performance in this emulation. Okay, but before we go into the details of the emulator and the in-lab testbed that we built at Surrey, let's have a quick look at the comparison between different approaches to enable networking research at in the LEO mega consultation. So first, if you want to focus on the transport layer performance and development on LEO network, then simulators like Hypatia or Hypatia might be a best approach for that. It's for quick development of a new condition control or a new transport layer protocol. So if you're looking for something like high fidelity, especially on layer one and layer two, a physical layer and MAC layer, of the protocol stack, then you might need to look at the hardware in the loop approach. So if you are interested in implementing like a new retransmission protocol, for example, in a layer two, or you are looking to implement like a new beamforming protocol in the physical layer, then you might need to do that on an actual hardware. So you might need to have a hardware in the loop in the lab to test this before implementing it on the actual satellite. I will talk about the hardware in the loop in the coming slides and how we achieve this in lab test our hardware in the loop test bed. But obviously you cannot do that with the emulation because it cannot give you this high fidelity of layer one and layer two. So as you can see, there's nothing that can achieve everything. So none of these approaches can achieve all the scenarios or can do everything. So here in SERI, we try to get the best of both worlds. So we try to combine or build what we call a SpaceNet testbed, which consists of three modules. So the first module is the measurement platform module, and then the hardware in the loop module, and then the emulation module. And we interconnect these modules to each other. So none of these are acting as standalone, but they are rather interconnected with other modules in order to get the best of all of these different modules. I'll spend that. Yeah, in the coming slides, I will spend the time talking about each and every one of these modules and how we implement them and what are the actual functionality of them. Okay, so let me start first by talking about the measurement platform. So the purpose of that measurement platform is actually to collect data sets that can be used as an input to the emulation module to make it more realistic and comparable with the real world LEO network. So specifically, we are building two data sets. So the first data set, we call it a volunteer measurement data set or volunteer measurement nodes, where we asked a set of volunteers. Actually, there are 8 volunteers distributed over a number of cities and continent. We asked them to connect a Raspberry Pi, or and some nodes we also send them Intel NUC machines to connect these machines or these computing devices to their Starlink terminals. So why Starlink? Because Starlink is the only commercially available LEO network that live now. So we send these NUC devices or Raspberry Pis to the volunteers, asking them to connect them to their Starlink terminals, giving this architecture here. So let me go with you around to explain this architecture. So what we have here is actually the Starlink router, and this is provided by Starlink. So every Starlink box actually comes with the router and a Starlink dish. And these are connected with each other through like a kind of feeder from the dish to the router. So the router itself can also is also providing a Wi-Fi connectivity, but it has also Ethernet cable. So you can connect Ethernet cable from that router to your computer directly, or maybe to another router, or maybe to another switch. So so it has this option of directly connected to the router, not through the Wi-Fi. So what we did is that we asked our volunteers to connect the Raspberry Pi or the computing machine that we sent to them directly to the Starlink router through an Ethernet cable. So we asked them explicitly to connect that through Ethernet cable because we don't need to worry about the wireless channel between the computing device and the router. So we directly connected to these routers through cables, Ethernet cables, and we're running the experiments on the active measurement experiments on that Raspberry Pi. So now what happened is that, so any experiment that you run here is actually go to the router, and then from the router to the dish, and from the dish it goes to the satellite. It could be the nearest distance, it could be anything. It's based on the on Starlink handover strategy, and then from that satellite all the way down to the nearest gateway or Starlink gateway, and this is what we call as a bent pipe architecture. So until now, there's no intersatellite links because it's not activated on any of the. It's not activated yet on Starlink terminals. So Starlink gateways is nothing but just like a farm of terminals. So Starlink is deploying like these kind of like farm of terminals across different countries. So for example, in the UK, there's 3 locations where Starlink has gateways where the connectivity from satellites terminate there. So what we are measuring actually in these on that computing device on the Raspberry Pi or on the Intel NUC. So we're measuring actually 3 things. We measuring the uplink and downlink throughput. We measuring latencies. These are mainly ping latencies, ping, and we measuring the packet loss experiencing on this bent pipe link or this bent pipe architecture. Along these 3 measurements, we also collecting kind of like context data from the Starlink dish itself. So Starlink has an API that you can query and collecting some context data, and these context data is something about the azimuth and elevation of the dish, maybe any obstruction that the dish can see, or maybe like also the latency to the nearest pop, or the latency to the Starlink gateway. What is the latency to Starlink gateway? So we're collecting this context data as well alongside the 3 active measurements that we do. So this is the first data set. So the second data set is actually the weather conditions data set. So we collecting weather condition using Open Weather Map API. It's an open source API that give you the weather condition on a city level. So in addition to that, we also have a fixed weather station to attach to some of these Starlink terminals. So we have access, as I said, to 8 Starlink terminals. Some of them we also attach to them fixed weather station. And we collect data from these fixed weather station to have more fine granularity weather information, and not just a city level, but also like very fine granular measurement or weather measurement data. So we use this weather measurement data as well to correlate the performance to the weather condition, and use that as an input for the emulator to make it more realistic in terms of the estimating the effect of the weather, for example, on the performance. So just to summarize here on this slide, so we have 8 volunteers distributed over 5 cities. 2 of them in UK, 3 volunteers in the UK over 2 cities, 3 volunteers in Spain, and we have 2 volunteers in United States across different cities as well. Okay, so let's move now to the second module and the Surrey testbed. After the measurement platform, so we have the hardware in the loop in-lab testbed. So this is like a collaboration work with our colleagues in Virginia Tech. So what we did actually is that we tried to have some, not an actual satellite, but a representation of satellite in a lab environment. So for example, if I would like to have a hardware representation for satellite, that could be like a 2 module or 2 modules. One of them is the computing device actually of the satellite, plus the radio device of the satellite. So, and this is what we've done here, is that so we have a bunch of single board computers. These could be Raspberry Pis, could be NVIDIA single board computers, could be any kind of like a computing device. And these single board computers act as a computing nodes of either a satellite or a ground station. And then we attach these computing nodes to a single port, to a software-defined radios, or SDRs. Currently, we are using USRPs. So, and these SDRs as acting as the radio component of the satellite, or the radio component of the ground station or the terminal. And then we emulating the channel between the ground station and the satellite, and this is the ground station satellite link. We emulating that channel using a channel attenuator, and that channel attenuator is actually a programmable channel attenuator, and we program that channel attenuator based on the location of satellite, the location of the ground station, the weather condition at this point of time, and then there's a module that program that attenuator based on these inputs. So what we simply done here is that we implemented a simple GNU radio module for layer 2 and layer 3 on these Raspberry Pis. And we use this GNU radio module to do a basic transmission between a representative of a satellite, which is a Raspberry Pi, to a representative of a ground station, which is another Raspberry Pi. So everything here is implemented in a GNU radio, and this is just a quick screenshot of the basic transmission, like a kind of like a bucket transmission between these two devices, the Raspberry Pi as a ground station and the Raspberry Pi as a satellite. So in the future, we're planning also to implement kind of like 5G-like stack for the MAC layer and the physical layer of these GNU on the GNU radio. So instead of having this simple protocol of a MAC layer protocol, what we currently have in GNU radio, we're planning to extend that further to be like a 5G compliant that we can run on these representative version of satellites and ground stations. Okay, so let me move now to the last piece, which is the emulation. So actually, in the emulation, we divided the emulation into into different layers. These are starting from the traffic generation, the traffic that we generate inside the emulation in terms of UDP traffic, UTCP traffic, or even ICMP traffic. And then we have a module for the constellation and emulation configuration. So what kind of constellation we are emulating, what configuration that we need to do in order to emulate that constellation. I'll talk about the details of that in the coming slide. And then we have three main modules here. We have the link characteristics module, we have the routing module, and we have the mobility management module. And then all of these modules are actually built on top of Mininet software, which is the virtualized environment that we use. Now let's talk about the details of each and every one of these modules. So I will start first by the constellation and emulation configuration. And here is just nothing but like an example of the configuration file that you need to provide to the emulation in order to do to start the emulation. So basically, here's this configuration file is divided into 5 parts. So the first part is about the constellation itself. So for example, what kind of constellation that you're planning to run? Is it for Starlink? Is it for OneWeb? Is it for Kuiper? Or is it for something completely new constellation that you're planning to send to space? So you need to define that here in this configuration file. So we use that operator name to get the TLEs file. So currently we get the TLEs file from Cellestrack. So Cellestrack is a website where we have TLEs file for most of the existing mega constellation or LEO mega constellation. If you have your own TLE files, then you need to put that here instead of the name of the operator. You just will put the URL of your TLE file. And then you need to define the number of shells. So for example, Starlink has different shells. Starlink has 5 shells. So here you need to define, are you emulating only one shell or multiple shells? And then you define that by putting the shell number here. So if it's only one shell, you put one, but if it is multiple shell, you need to put comma and then the shell number that you want to emulate. Like for example, 1,4, for example, that you will emulate 1 and 4. And then for each shell, you need to define some parameters of that shell. And these are just from the FCC filing. So these are the number of orbits, satellites per orbit, elevation angle, inclination, and these parameters you need to define for each shell. And these are just you can extract them from the FCC filing. So if you would like to emulate more than one shell, then you need to repeat that that block here for the additional shells. Another thing you would also need to configure is actually the topology. And when we talk about the topology, we're talking about two things here. It's either the one thing is the ground station satellite links handover strategy. So how the ground station will decide on which satellite to connect to and how to hand over from one satellite to another satellite. So this is the handover strategy that we mean here. So you need to define that. So currently in the emulation, we implemented two handover strategy. The first handover strategy is actually based on the distance. So the terminal get connected to the satellite, the nearest satellite. I mean, the minimum distance, the nearest satellite. Or this is one strategy. The second strategy is that the terminal or the will be connected to the satellite based on the longest attachment time. So the terminal will choose the satellite that will remain connected to that terminal for the longest period of time. So these are the two handover strategy that we currently implement in the emulation, but this is just in a module and easily can be easily extended for other strategies. ISLs is actually the inter-satellite links. So the default inter-satellite links topology is grid, which means that each satellite will have 4 connectivity, 2 to the satellites in the same orbit, and 2 to the satellite in the adjacent orbits. So this is the default ISL topology and the emulation. Now, if you only want to emulate the pin pipe architecture, you don't want inter-satellite links, then you replace that grid by no. So if you replace grid by no, that will be pin pipe architecture. There will be no inter-satellite links. And then another thing is the routing. So how we do routing between different satellites. Currently, we implementing a static routing. And then we define the IP range for these for the different satellites. Another related to the routing is actually the inter-domain routing, or what we call the cross-constellation routing. Now, imagine that we have emulated Starlink Mega-constellation on one machine, and then we have one web on another machine, and we want to route the traffic between these two Mega-constellations. And this is what we call inter-domain routing or cross-constellation routing. So there is different strategies to do that. So the simplest one that we implemented here is that based on what we call a border gateway. So we have a terminal or a ground station. It acts as a border gateway between these two mega constellations. So for example, if a ground station or terminal in Starlink would like to transmit traffic to a ground station or terminal on one web, it will go through what we call a border gateway, which is responsible to connect these two mega constellations. And here we define what is exactly the border gateway in this emulated environment. The second component of this file is actually the ground station file, or the ground stations. And these are just a file that contains the coordinates and elevation of the different ground station that we want to emulate. So if you would like to emulate a ground station, a specific location, you only need to provide the lat and long and the elevation of that ground station. And then you need to define the simulation parameters, which is the start time of the simulation, the duration of the simulation, the resolution, how fast you would like to update the satellite location. For example, is it every 1 second? Is it every 100 millisecond? is it every lower than that, like 10 milliseconds? So you need to define that here. And then you need to talk about the application. So what kind of application that you would like to implement on the top of this emulation? Is it like iPerf? So currently we implemented two basic applications. We have iPerf and reverse iPerf, obviously, and we have Bing. And then we need to define the source and destination, duration of the experiment, condition control. If you implementing iPerf, here you can vary the condition control. As of now, we're relying on the already existing Linux-based condition control. Here I'm talking about Cubic, BBR, Reno, Veno, and Illinois. So these are the most famous or existing Linux-based condition control that we can test over this emulator. And then you can say if you would like to have a background traffic while doing the simulation, and the output, how you would like the output to be look like. And then the last piece is just the location of the output and the output files, where these output file will exist. So this is the first part about the configuration of the emulation and consultation. Now let's move and talk about the main component on the main modules in this emulation, which is one of them is the link characteristics. So when we talk about the link here, we're not talking only about the ground station satellite link, but we also talk about the inter-satellite links. And how we define the link, we actually define the link based on three values: based on the latency of the link, based on the actual capacity of the link, and based on the signal to noise ratio that the link is experiencing. And then in order to understand the signal to noise ratio, we need also to compute the link budget. And here I'm talking mainly about the link budget of the wireless channel between the ground station and the satellite. And to calculate the link budget, we actually relying on the RF parameter that is provided in FCC filing. Here I'm talking about what is the TX power for the satellite, what is the gain of the terminals, what are the type of antennas used, what are the vertical and horizontal beams of the antennas. So we use all this information to calculate the link budget, and based on the calculated link budget, we can calculate the SNR experienced on that SNR, on that ground station satellite channel or wireless channel. So latency, capacity, and SNR. But there's other variables that you can vary in the simulation on the emulation. So you can play with the cell density. So you can emulate some density cells. So that will affect the capacity performance of the achievable link between the ground station and the satellite. And also you can add the weather effect. So by default, the weather effect is not added, but you can, it's implemented. You can add this weather effect on the performance to see how the performance will change. So currently we have two modules for the weather effect. We have the default one, which relies on the IT models for the weather effect, and we have then the other module, which is we implemented that based on the real world weather data that we collect. So this is it's a module that use the real world measurement weather measurement data alongside the performance measurement in order to get better clarity or on the effect of the weather on the performance. So you can either use the ITU models that we have already in the code, or the new implemented weather effect that relies on the actual real data, not on the mathematical models. Okay, the second module is actually the routing module. So in the current emulation, we pre-compute the routes. So because these satellites are predictable, so the location of the satellites are predictable in the future because they are orbit in a fixed orbit. So we can know the location of the satellite ahead of time. So this is what we actually do. We pre-compute the location of the satellite, and then based on that, we pre-compute the routes between all the possible routes between any source and any destination. And we use that, we input that to Mininet. I will talk about that in the coming slide. So for now, we do static routing. It's mainly shortest path routes, and that shortest path is based on um, three categories. Again, this is configurable. By default, it's based on latency. So the shortest path that achieve minimum latency, but that can be changed to capacity, and that's the path that achieve the highest capacity, or hop count. So the path that has lower hop count. Um, so these are all these are implemented and can be configured while running the simulation. Another routing functionality that we have here is actually what I talked about before, is the inter-domain routing and cross-constellation routing. So currently we're implementing that through what we call a border gateways. So we have a fixed gateways on the different mega constellations, and we route the traffic through these gateways. But as I said, there might be other approaches, like instead of having a border gateways, we might have a border satellite. And now the question of how efficient or more challenging this compared to the border gateway approach is something that's still open for research. And also in the future, we are looking to integrate not just a static routing, but more like a dynamic routing algorithm, something like a BGP and OSPF. And the good thing is that because everything is fed back again to Mininet, and Mininet is a bunch of virtual machines or virtual nodes that based on Linux stack, then that makes implementing these BGP or OSPF routing protocol is easier, because if you have an already existing implementation for BGP or OSPF on Linux, you just can plug that into the emulation, and then you can understand the performance of this dynamic routing algorithm on that emulated environment. The last module before we go into Mininet is actually the mobility management. So, and here is we're using, as I mentioned before, we're using the TLE files that we got from Stellistrack to compute the future location of the satellites. And that is important to understand the topology, the changes in the inter-satellite links or the changes in the ground station satellite links. And so based on that, also we can understand how the topology change with different resolution, like a 1 second resolution or 100 millisecond resolution, or even lower resolution up to 1 millisecond. And then, as I said, we rebuild the topology every predefined interval, which is the resolution. And then this topology, as we talked about that before, it could be the pin pipe or the inter-satellite links. And then we, as I said, talked about that before, is the handover strategy for the ground station satellite links. Until now, we have two implementations: shortest distance and longest attachment, but also other strategies like SNR-based can be easily implemented. Okay, so the last module is actually the Mininet. So once we pre-compute the routing, configure once we configure the constellation, pre-compute the routing, build the topology, and configure the link characteristics, we need to feed back all these information to Mininet, and Mininet will set up the nodes, and these are just a virtualized process. And these nodes is a satellite and a ground station, and then build the topology between these virtualized nodes. It's both the inter-satellite links and the ground station satellite links, and then configure the interfaces or these links through netim command in Mininet. So that mainly we're configuring the capacity of the links and the latency of the links. And then we run the application on top of that, and then there is a background loop that updates three things. Actually, it updates the topology. So every predefined interval, which is the resolution that we define in the configuration file, we need to compute the new location of the satellites, see if there is any change in the topology, and build the new topology, and then compute the new link characteristics in terms of latency and capacity, and then see if there is any change in the routing, and update all these information, link characteristics, routing, and topology in Mininet. And this is a background loop happening while the application is running. So this is like a quick overview on the testbed that we built in Siri. That's conclude my talk, and I'm very happy to take your questions. Thank you.